I wanted to thank Dr. Nussbaum for coming today to speak to us all. Dr. Nussbaum is the Chief Medical Officer of Invitae. He's board certified in internal medicine, clinical genetics, and clinical molecular genetics. And I think Sharon actually, sorry, I just got a message. Would you like to give the introduction?
Not for me. No, good.
Oh.
Go ahead.
Okay. Sorry. Anyway, Dr. Nussbaum is a fellow of the American College of Physicians, founding fellow of the American College of Medical Genetics and Genomics, and served on the board of directors from the American Board of Medical Genetics and Genomics, and has been a director and president of the ASHG. And today he's going to be speaking to us all on residual carrier risks and flawed data. And Dr. Nussbaum, if you could take it away.
Thanks.
And the only thing I would say is that Bob was one of the early ClinGen PIs before he made his switch to Invitae.
Thanks, Sharon. So I want to talk to you today about some work that I have done and thinking about on ancestry-based residual risks in carrier screening. And I refer to this as the fallacy of false precision, that using implausibly false statistics to give the appearance of truth and certainty, when in fact it's based on such uncertain information as to be not very valuable. These are my disclosures, Invitae, Genome Medical, Maze, and Pfizer Pharmaceuticals. And these are my own opinions and don't reflect those of any of the companies for which I work or consult. So this work is mostly that I published about a little more than a year ago in prenatal diagnosis with my co-authors, Nate Slotnick and Neil Risch. Here's the PMID. If you want more to dig in more details into what I'm talking about, it's all in there, including in a bunch of appendices. So what is residual carrier risk? It's the probability an individual is a carrier for a recessive disorder despite a negative carrier test. And residual carrier risks have been used in carrier screening counseling for over 2 decades. Where do they come from? It really comes from the dawn of DNA-based carrier testing for cystic fibrosis. And what happened was, because of the technology available at the time, they screened for 25 of the most common pathogenic variants present in more than 1 in 500 people. That was kind of the cutoff in the US general population, and also in certain subpopulations, such as African American, Black individuals in this country, or Ashkenazi Jewish individuals. And the problem was that because they limited it to 25 pathogenic variants that had a reasonably known carrier frequency, they were quite sure that there were other pathogenic variants, over 900 that were described, that were omitted from screening because they wanted to reduce the complexity and cost of the test. In other words, just hit the 25 most common ones. And the problem, of course, is that non-Europeans had a different spectrum of pathogenic variants than European origin people for cystic fibrosis. And so that using that 25 pathogenic variant panel would allow even more people of non-European ancestry to test negative for the panel, even when they were carriers for cystic fibrosis. So the guidelines that were published at the time were that providers should define as accurately as possible, based on current knowledge, the residual risk that the person tested could be a carrier of an untested or unknown mutation. This recommendation was made out of concern that practitioners and patients alike were unfamiliar with the concept of a clinical false negative in genetic testing and needed to be alerted that false negatives were bound to occur. And an additional recommendation that was made at the time was that different residual carrier risks be provided that are tailored to an individual's racial/ethnic background. That's quote unquote, that's from the paper, without really specifying how one was supposed to determine accurately what an individual's racial and ethnic background is. Well, what's changed since cystic fibrosis screening began? Well, the big change is that we're screening by sequencing. Screening began with the most commonly known pathogenic variants, but initial screens did not detect other known pathogenic variants in various populations that were left off the panel. Pathogenic variants that we know must be in various populations, but we can't detect them because they're outside the reportable range of the test. Or variants that we actually will see when you sequence, but they're currently classified as variants of uncertain significance, but may eventually be classified as pathogenic. And I kind of refer to those in the paper as proto-pathogenic variants. They will ultimately be reclassified. Of course, at the time, you don't know that. You only know that they're VOSs, but they will have an impact on which variants can be detected. So with sequencing, we can detect all known pathogenic variants, but we don't report variants that are outside the reportable range or VOSs that will ultimately be classified as pathogenic, although we don't know that at the time. So numbers 2 and 3 are the source of the residual risk after a negative carrier test by sequencing. So it's not that we know that we're missing certain variants, the way the initial 25 allele panel was constructed. We're going to try to find them all, but this is sort of the known unknowns. We know that there are going to be variants. We don't know how many or what they are outside the reportable range. And we also know we're going to find VOSs that we're going to have to figure out what to do with them with additional data. So that's how sequencing has changed the landscape. Here's an example. An approximate disease incidence of cystic fibrosis was estimated in Japan, and I should say estimated, between 1 in 100,000 to 1 in 350,000. I think it's kind of interesting that in a country with an advanced economy like Japan, they actually still could not provide a more accurate estimate of the cystic fibrosis disease incidence. But if you take that, average it out, it works out to be an average carrier frequency of about 1 in 200, 1 in 197. Turns out that more than half of all Japanese cystic fibrosis patients, actually Asian patients, but Japanese in particular, don't have a pathogenic variant that's represented in the fixed variant United Kingdom newborn screening panel, the initial panel that was put there. So a negative United Kingdom fixed variant test for a Japanese individual lowers the residual carrier risk only modestly, from 1 in about 200 to 1 in about 440, because so many of the known pathogenic variants are just not on that panel. Then a previously unrecognized CFTR deletion mutation was found to account for almost half of the pathogenic CFTR alleles in Japanese CF patients. If you now include that deletion mutation on a panel, a residual carrier risk for a Japanese individual testing negative for both this common deletion and the UK carrier screen falls to 11-fold, to 1 in 2,200. So you can see that knowledge of what the variants are in the population so that you can test for them by sequencing has a huge impact. And the other thing the other take-home message from this is, if you go into a population and you test affected individuals, you do diagnostic sequencing in affected individuals, the most common alleles that cause the disease are the ones you're going to find first. So you get more bang for your buck as you go in there and get started with just finding out what are the spectra, what is the spectrum of variants responsible for a particular disease in a particular population. So what is residual carrier risk? How do you actually calculate it? It's equal to twice the difference between the population frequency, which we call Q, of every pathogenic variant, known or unknown, all of them, in a population, which I'm calling QPath, and the frequency of all pathogenic variants that are known and can be detected by the sequencing-based carrier test in the population. So that difference, QPath minus Q detectable, and of course it's twice that, because with the Hardy-Weinberg law, and if you let P be approximately 1, that's really where it comes down to. The residual carrier risks are calculated as being twice the difference between QPath and Q detectable. Well, where do QPath and Q detectable come from? QPath is generally derived from measuring the disease incidence in a population and applying Hardy-Weinberg. You assume that QPath squared is going to be the incidence of disease, so QPath is the square root of I. And I could differ between different groups, but that's where QPath generally comes from. How about Q detectable? Well, that depends on how much sequencing has been done in this population, how good are the measurements of frequency, pathogenic variants. Since these pathogenic variants tend to be pretty rare, they may not be in large databases such as Genome-Wide. And so figuring out what the actual frequency is of the variants that you can detect is quite complicated and can also differ among different groups. Depends a lot on how much research has been done on the disease itself and how much population genetics has been done on the disease itself in order to be able to measure Q detectable, QDET. So here are the challenges. First of all, disease incidence I. You have to have that if you're going to measure QPath, right? But measurements of I are inaccurate or unavailable for many of the world's populations. I'll show you some examples of that in a minute. Second, you're inferring QPath from the disease incidence I by assuming Hardy-Weinberg equilibrium. That could very well not be justified in many populations where there's non-random mating. Remember, Hardy-Weinberg depends on non-random mating. And if there is not, it depends on random mating. So if there's non-random mating or there's consanguinity, they will artifactually raise disease incidence over and above what would be expected simply from the square of QPath. So QPath will actually not be the square root of I. It's actually less than the square root of I when Hardy-Weinberg equilibrium does not apply, when there's consanguinity in particular. Now, how about measuring QDET? We rarely know the true population frequency of all of the pathogenic variants we can detect. And there's going to be a group of variants there that we know about that are classified as VUSs. And they're not going to contribute to Q detectable right now, but may in a year from now, or 2 years from now, or 3 years from now. So that when that happens, Q detectable is going to change. So the idea that you can establish a residual carrier frequency risk today and not reevaluate it and change it over and over again as we learn more about the detectable variants in the population and as we figure out more and more about the VUSs is just simply naive. So let's talk about measuring disease incidence I. Cystic fibrosis is sort of interesting because there's newborn screening in many of the first world so-called advanced countries. And there are specialized cystic fibrosis clinics where all patients with cystic fibrosis go and get care from places like in the EU. So the incidence of cystic fibrosis in many Western European countries is pretty accurate. But measurements of cystic fibrosis incidence are challenging for most areas of the world lacking these programs. Ascertainment's incomplete, and the estimates of incidence are approximate and are probably artifactually low, which means that your estimate of QPath is going to be too low. In Latin America, there are only 4, and this is as of 2020, there are only 4 countries, Brazil, Uruguay, Argentina, and Chile, that had national CF screening programs, did not have organized CF clinics, but you can get some estimate of nation-specific incidence from newborn screening. But even with newborn screening, if you look at Brazil, the estimates of CF incidence range from 1 in 1,600 to 1 in 14,000, depending on the Brazilian demographic under consideration, whether you're north or south or you're east or west, what the ancestry of the people are, and of course, Brazilian demography is highly admixed. And so you have this wide range of CF incidence. Well, if you have someone sitting in front of you who says they're Brazilian, what are you going to use as the incidence from which you're going to derive QPath to make the residual recurrence risk calculation? And if you go beyond cystic fibrosis, other rare conditions, it's even harder. There's newborn screening for some, of course, in some countries, but that's generally mostly for metabolic disorders and for a few others. The vast majority of genes and disorders for which we're doing carrier screening. There is no newborn screening, and the incidence measurements are really very, very difficult. So, second, is Hardy-Weinberg justified? Here I want to give you an example. The population of the United Arab Emirates consists of subgroups. About a quarter of South Asian from India, about 12% Pakistani, etc. Intermarriage between many of these groups is limited for reasons of religion or country of origin, and there's a significant amount of consanguinity. The overall incidence of cystic fibrosis in the United Arab Emirates is 1 in 15,876. That's great, but that's just this average. That differs greatly among these ancestral groups. An average carrier frequency of CF of 1 in 63, which is the square root of that 1 in 15,000, is likely not applicable to any individual in any of these subgroups. Now, assume an ancestry-specific residual carrier risk is actually accurate. Let's make that assumption. Suppose you have an accurate measurement and you're applying Hardy-Weinberg is justified. Okay, it's justified. If the mating is pretty close to random and you're okay. And you have an accurate, up-to-date measure of the frequency of pathogenic variants detected by the carrier test in that population. So you have an accurate residual recurrence risk. Suppose that, and as I just explained to you, I think these are all actually quite dubious, but let's make that assumption. Now what? How do you know that the patient sitting in front of you actually matches the ancestry-specific residual carrier risk, which you just so carefully calculated from the incidence and from the Q-det, et cetera? If the patient's of mixed ancestry, which data do you use? Well, you can use self-reported ancestry, but of course, this is a really nice paper that looked at over 93,000 individuals undergoing expanded carrier screening. And 9% of patients self-report an ancestry that's actually discordant with their genetic ancestry as defined by allelic markers. In other words, our typical SNP analysis for trying to determine ancestry, continental ancestry, or even subcontinental ancestry. Concordance between self-reported ancestry and genetic ancestry was actually quite low in a number of groups. And almost 1 in 10 patients were unaware of their genetic ancestry. So just asking people, what's your ancestry, and saying, whatever you say, I think I've got a residual carrier risk that matches your ancestry. I've calculated it from the incidence from where you say you're from, et cetera. And I think Hardy-Weinberg's fine, and I think we know what the frequency of detectable variance is. That's fine. How do you actually know that this person in front of you fits the population from which you've made this, as I said, somewhat dubious residual carrier risk calculation? You really don't. It's very hard to do. Furthermore, the way self-reported ancestry information is requested can impact accuracy. Most of these race, here's an example from a paper order form for genetic testing. Race, ethnicity, Ashkenazi Jewish, Asian, Black, French, Canadian. I mean, it's kind of haphazard, and exactly what self-reported ethnicity or ancestry you choose is determined to some extent by what are you offered, what's here. Then there's this other thing, so you can fill in something, but who knows whether we actually have attempted to calculate a residual carrier risk that matches whatever someone puts in other. And this has been demonstrated. This is a paper by Dyson on ethnicity questions and antenatal screening in England. And what it basically showed was that depending on the structure of the questionnaire, you got different answers. So self-reported ancestry can be affected by how you ask the question. So, all right, suppose you say, all right, I'm not going to ask you. We're going to use genome-wide SNPs to determine ancestry. Let's do that. So, as you all know, there are ways of using principal component analysis to look at a bunch of SNPs. Here's just one example I pulled out of the literature. Using a bunch of SNPs and then looking at the frequency of the alleles and seeing how closely the first and second principal component or eigenvectors match to allow you to attempt to cluster individuals. Each little circle there is an individual, and try to cluster individuals by similarity in allele frequencies. For these, this was done on almost 23,000 SNPs. And you can see that people who say they're of African origin, and we think they're originally from Africa, they're all kind of up in the upper right-hand corner, and the people who say that they're Caucasian, and of course I don't use the term Caucasian because I think it's a ridiculous term, but it's white, is up in the upper left, but this is what was published, so I'm just showing you what's here. And then Hispanic, which I'll show you in a minute, it isn't really an ancestry at all. And then finally, other in the bottom left-hand corner. It's possible, if you accept the ancestral backgrounds of the people who are getting the SNP testing, that you can kind of cluster them this way. And this is how ancestry is done based on SNPs. And I think it's, as reasonably well accepted, given all of the problems with doing this, that that it can be. But here's the problem. This is a paper from one of my friends, Esteban Burchard from UCSF. This was looking at 96 self-identified Puerto Rican individuals. People all said, yeah, I'm Puerto Rican. And he just looked at 3 continental ancestry: Native American, which is the dark on the top, European, which is sort of the light in the middle, and then African is the bottom. This is done with Genome-Wide, with 116,000 SNP loci from across the genome. And these are just organized essentially by the contribution of African ancestry from the left to the right. So if look at individuals 1 and individual 96. Individual 1 is 15% Native American, 77% European, and 8% African, according to their SNPs. And individual 96 is a little more Native American, 20%, significantly less European origin, 30%, and significantly more African origin. Okay, so these 2 individuals, what CFTR, residual carrier risk, should one use? Well, these are global ancestries. What really matters is, what is the ancestry, what is the origin of the region around the CFTR locus? And this does not tell you that. So you can use average genome-wide ancestries, but it's not really answering the question that you need, and it has to be different for each individual gene and disorder that you're doing a carrier test for, because the ancestral origin could be very different. These 2 people could have their these 2 individuals, 1 and 96, could have their CFTR locus in both cases of European origin, in which case they would have very similar kinds of calculations done for them. If you look at individuals 92 and 93, they have almost nearly identical admixture. Okay, from which ancestral group were each of their CFTR loci derived? Well, individual 92 could have a CFTR locus of African origin, and individual 93 could have it of European origin. So it's going to be completely different, even though their admixtures overall, genome-wide, are very similar. So all of these indications, as Nathan Slotnick and Neil and I were thinking about this, about the same time, this practice guideline came out from Genetics in Medicine, Greg et al., where they basically said, hey, look, carrier screening paradigms should be ethnic and population neutral, and more inclusive of diverse populations to promote equity and inclusion. Now, I'm going to get into more detail about what that means. But what they're basically saying is the problems with calculating residual carrier risk and the problems with assigning a particular calculation you've made for a particular group to an individual. Does that individual actually have the locus coming from that geographical origin? Just makes this so fraught that you're really doing a lot of calculations that they really don't make any sense. In other words, I see this as being false precision. So let's just switch gears a little bit now and talk a little bit more about the clinical side of this. And this is going to be quite controversial, I think, which is, suppose you say, okay, look, we're not going to do any ancestry-specific residual carrier risks. Does offering a residual carrier risk at all of any particular value for patient management? Should we be offering anything? So this is a little calculation that I did. Suppose a pregnant couple would have to have a risk, a residual risk as a couple, a residual risk of having a child with this disease, that of a risk that's greater than 1 in 500. And where did the 1 in 500 come from? It's really thought to be the actionability threshold for prenatal testing, prenatal diagnostics, having to do with complications from amniocentesis or CVS, et cetera. You can lower that. These numbers came from a number of different review articles. You could lower it to 1 in 1,000. It really doesn't change the ultimate conclusion. If both members of the couple test negative and have therefore have some residual carrier risk, in order for their residual carrier risk to trigger a prenatal diagnostic test, it would have to be greater than 1 in 11. And there simply are no residual carrier risks greater than 1 in 11 when you do sequencing of these genes. Of that, I think we can be quite confident. That number is very, very high. And we knock the residual carrier risk way down below that. Now, suppose one individual in the couple is a carrier and the other individual tests negative. Then the negative testing patient or individual would have to have a residual carrier risk greater than 1 in 125. And there also, with very few exceptions, that is too high. So what I'm saying is that residual carrier risks are already lower than would be needed to trigger a prenatal diagnosis, given the cost-benefit ratio of the complications from a prenatal test. Now, as I said, this is controversial. One can argue, well, risk is in the eye of the beholder. Maybe the risk for miscarriage for somebody is of less significance than the risk of having an affected child. And so you can't equate decision-making based on risk alone. And I will accept that. And that's why this really needs to be thought through and discussed. But I guess what I'm really saying is, for the vast majority of the time, when both patients test negative, the residual carrier risk really drops their chance of having an affected child so low that the actual specific number that one would generate and give to the patient, sit there in the room and say your residual carrier risk is XYZ, is so low that I'm not sure that it has any significant clinical benefit. So here's my conclusion. Ancestry-specific residual carrier risks have limited validity and utility. They often rely on missing or inaccurate incident data. They depend on an assumption of ideal Hardy-Weinberg equilibrium, which in many populations is not the case. And they have built-in uncertainty because of the changes in which variants you can detect by sequencing and how they're interpreted change. And assuming geneticists think they have an accurate ancestry-specific risk, applying them correctly requires knowing the ancestry of the individual at the locus in question. And we don't know that. You can't ask them, you can't do that by asking people, and you can't do it by genome-wide. Now, I've talked to some people who say, oh, well, we're going to use genome-wide SNPs to actually look at the region around each gene. But I want you to imagine now what's going to happen is you have 500 genes, you do a genome-wide SNP analysis, and then you have to go gene by gene, look at the linkage disequilibrium block around that gene, and figure out whether you have sufficient number of SNPs in and around those to have a reasonable confidence that you actually know the ancestry of that region of the genome that the gene in question has come from. That's a lot of work. Finally, where is the evidence that the absolute value of the residual risk and the variation in that risk due to ancestral background significantly impacts clinical care or management in a real-world setting? I'd say that evidence is pretty limited. So these are my recommendations. I think ancestry-specific residual carrier risks are examples of false precision and should be abandoned. Even ethnic or population-neutral residual carrier risks are mostly guesswork, using incomplete data and assumptions about random mating, and are of unproven clinical utility, as their absolute value rarely exceeds the threshold of being of use in clinical decision-making. They can also be abandoned in the spirit of honest communication between patient and counselor. In other words, you don't sit there and tell people some number, oh, your residual carrier risk is 1 in 445, as if you really know that it's not 1 in 600 or 1 in 280. You really don't. So, is the juice worth the squeeze? I would say no. So what juice is worth the squeeze? I would say if we want equity and inclusion for carrier testing, our number one job is to do genetic testing, diagnostic testing in affected individuals in every population around the globe. And let's find out what are the pathogenic variants that are active, that are present, that are causing disease in those populations, so that we now know about them. We can interpret them, get them out of Vussland, get them into pathogenicity. And now we'll have a very high Q detectable that is that may be different from population to population. But remember what I said. The big advantage here is if you go into a population that's been understudied, the first pathogenic variants you find are going to be the most common ones when you analyze and sequence patients with genetic disease. So they're actually pretty low-hanging fruit. You get them out. Then you know you can provide them to couples from those groups, from those populations, and have essentially a worldwide catalog of all of the variants that can cause disease X, Y, or Z, regardless of where you come from. Your area, the variants that may be increased in the place where you come from compared to where someone else comes from, they're there. We have them in the catalog, and we can therefore provide the appropriate clinical care for you. And with that, I'm going to stop.
So, Bob, I'm not sure you
Yes.
want to completely stop sharing in case people have questions. There's lots of comments already in the chat.
Oh, okay. Okay.
And I will say I completely agree with your last point. And the one quick point I was going to make is that the carrier screening is often being done, for example, in the US population, to people who have come from other parts of the world. The cases are often actually in those countries. And so I was going to start off with a question for you, because I completely agree with your last point, is, you know, what is the best way to be able to sequence the cases?
Yeah. So, you know, that's really a population genetic / epidemiology effort, which should be carried out by the geneticists and the the public health people in these different areas. It's not that expensive to be able to do this testing these days, and we're talking about rare diseases, and so there's not huge numbers of these folks. We're not talking about doing a million normal, or I should say unaffected individuals in a population. So I think it requires, it's the kind of thing, for example, we've started doing with people affected with various genetic diseases in Africa. They are desperate to have someone provide them with low-cost diagnostic testing for patients with their disorders. I think the so-called first world should say, look, Sharon, just as the point you made, we have people in our population, we have fellow citizens who've come from all over the world. We should be finding out what variants cause these diseases from all over the world. And it's a commitment that I think should be made and should be done with dispatch, in collaboration with, in full cooperation with the physicians in those countries.
Okay. So, Alex, Ioannidis had a question about, I'd like to understand why population incidence rates are a computational construct as opposed to like data.
So Sharon, that was actually in reaction to an earlier comment that
Okay.
if you
So go ahead, Anna, you can start the discussion.
Oh, well, Alex, and you could jump in, was saying, well, like, the classic response to you pointing out that we don't know basically like the haplotype structure for any given individual. For example, the CFTR locus would be to use local ancestry inference and just, then you could pull out the kind of ancestral background around the particular gene you're interested in.
Yeah.
And then my comment was just that I don't think that'll be that helpful, because this whole notion that we've got these pure populations that we can kind of get at via local ancestry, that's what I think is a construct. And then you would have to know what the incidence rates were in these constructed like pure populations.
Yeah, I agree with you completely. It's doable, but the question is it worth doing? You'd have to do it. You'd have to do it for each locus where you're doing a carrier test, and that's going to be different in different individuals. And of course, we're not haploids or diploids, and so we're going to have this problem of having the two alleles coming possibly from different ancestral backgrounds. So, and then you end up with this, ultimately, and that's why I call this the fallacy of false precision. Yeah, you can do all that, but ultimately, does it really provide you with useful information, or does it just give the appearance of being more sure or being more certain of what the carrier residual carrier risk is? So I think the points you made are absolutely right.
Yeah, and I will turn to Alice next, who had a different question, but I do just want to highlight, because you went over it quickly, the Japanese example of that deletion, that there are, one thing that's always been true of genetics is you don't know what you don't know until you find it, right? And so for hemophilia, right, and it's a different example because it's a recurrent mutation, but half of the severe patients were undetectable until somebody figured out it was an inversion, right? And so we have this, we have this sense of what we might be missing, but you could easily have a population that, as you gave that nice example pretty quickly about in Japan, where in fact, once we found that deletion, then we dramatically change our ability to predict. So I think, again, just highlighting the need to sequence, deeply cases.
Yep.
Because in that case, it wasn't that you were missing a whole bunch of alleles, you were missing one major allele, as I understand it.
That's right. Yeah.
So Alice, you had a different question. It's pretty long in the chat. So do you want to just say what your discussion point was?
Sure. Well, they're actually sort of two slightly separate questions. The first one was, I think maybe this is the second question I put in the chat, which is more relevant to this topic, which is whether we could use this clinical use case as a framework to quantify what we really need to focus on in the population genetics and the research side, as you said, that needs to kind of do the sequencing. In the Pangenome Project right now in the US, we're trying to nail down a framework to quantify what is the greatest need. So where's the sort of key clinically relevant missingness from the databases? So I just wonder, Bob, if you thought about that as my first sort of question.
Yeah, I think so. I see two points. One is you start with the patients who have these diseases. First of all, the fact that they don't know their genotype, you actually don't know that the defect is in a particular gene and what those particular variants are, is a real gap. I mean, these folks should have accurate molecular diagnosis. And I think that it's very efficient to figure out what the variants are that cause disease by sequencing the affected individuals. And as I said before, the most common ones you'll get first. And so it's going to be a pretty rapid accumulation of very valuable data. The large population sequencing, I see some ways as being the exact opposite. What it's designed to do is to find common variants that are therefore unlikely to be associated with disease. Now, of course, you can't prove that until you have a lot of data. But just to know what are all the common variants around the world that are unlikely to be disease causing because they're so common is also very, very valuable information. So I see this as being two different thrusts. But I mean, for me as a physician, I go sequence the affected people first. That's where the biggest bang for your buck is going to be.
Right. As geneticists, we always go for the cases. So why don't I let Alex, because he had a comment about that, and then Alice, I'll let you ask your other question. So Alex, you wanted to make a comment?
Well, I just had a quick comment to branch off. I'm coming. A great talk, by the way. I really enjoyed this. This is super interesting to me. And it's something I've thought about, so I want to hear what you think. But I'm a little biased because I designed a local ancestry method, so just bear with me on that.
Sure.
But diploid local ancestry is not a problem for us. We can get the phasing accurate, in small segments anyway. So that you can have. Now, whether it's useful overall, I'm interested in your thoughts on it. I do think that unsupervised population clusters very clearly exist in some cases. We can see that with various unsupervised methods, and we can characterize them as having very different allele frequency distributions. So it seems to me that sometimes the haplotype background that something is sitting on might be useful, especially when we're not really sure. I think as Sharon was saying, what might be causal, but we kind of know that this haplotype, if it's coming in a Lebanese, background, seems to have a different, brain. But I'm just interested to hear your thoughts.
Yeah, but my thoughts really are that I accept that that's possible to do all that, but then you still are faced with the problem of, do you actually have an accurate measure of the incidence of that disease among the Lebanese population? And is that sufficient to figure out what the Q path is when there's substantial non-random mating going on in that population? So you're going to have problems with figuring out what the residual carrier risk is from these allele frequencies in that population, even if you can accurately say, oh yes, that locus in this individual has a very high likelihood of being of a certain ancestral background. You're still faced with the problem that you actually don't have a very good estimate of what you need to know from that ancestral background.
And is that partially a data acquisition problem, or you think it's unsolvable? And in that sense, not worth solving.
It's a data acquisition problem. Because we know that there are some disorders in some populations, through the use of newborn screening and through the use of specialized clinics, we actually have a pretty good estimate of what the incidence is. Now, you're still faced with the problem of, well, how much non-random mating is there? But that also actually you can estimate from population studies. So it's a data shortage. But I'm just still not convinced that knowing that 1 in 250 versus 1 in 350 versus 1 in 450 makes any real difference clinically.
Okay, Alice, your other point?
Yeah, so my other question was, if we sort of accept that, we don't have enough information to give accurate estimates in some populations, but we do have enough information in others, is there a case to be made that you could still do sort of standard practice, but then add sort of an uncertainty metric or some sort of reporting that says, look, we're really sorry, we are not able to accurately give you residual carrier risk because this is your background and it hasn't been represented in population databases.
Yeah, I mean, one could do that, and that to me that has the appeal of being more sort of, what do you call it, the truth in advertising about the actual figures that are being used. So that's kind of appealing. But for me, once again, it really comes back to that people have terrible problems with understanding what probabilities are anyway, and for example, I had one person suggest to me, well, don't just give a residual carrier risk, also give the 95% confidence limit on that carrier risk. Well, I can just imagine trying to have a genetic counseling session where you're talking about that with 95%.
Well, and I think it
confidence
still does get back to the mixed ancestry issue. I mean, you'd have to then do ancestry analysis and things like
Yeah.
that. But I think maybe we'll give Barbara Koenig, because she had sort of a big picture question.
Yeah.
The last question. Barbara?
Sure, thank you. Very great talk, Bob. As you were talking, I was just trying to imagine, especially given the recent WHO report on trying to imagine sort of global genomics. Can we imagine or think about what kind of public health structure would be needed to collect the information needed, on the highest, the variants that are the most important in different countries around the world?
Yeah, that's for me. That's a very hard question, because it's not really. I've never put together an effort like that, and I don't know that much about what it would take. I mean, just at a minimum, you would have to have people on the ground in these countries who are familiar with medical genetics and are comfortable with counseling and can counsel in a culturally appropriate way to the people who are getting this testing done. You can't just go in there, swoop in there, grab blood samples and generate this stuff so that we know what's best to do for the people sitting in our country. Meanwhile, leaving these, I mean, that's just not acceptable. So to me, that's the minimum, is that it's got to be appropriate to the people that you're taking the samples from. They know what it's for. It helps them. It gives them information. They get counseling. They get information about what's causing the disease in their family and their loved ones.
Right, because many of these disorders are cause early demise in the newborn period, particularly if you don't have advanced medical care, even if you do for some of them. And so you're more likely going to have to be testing the parents who've experienced these losses, as opposed to having the infrastructure.
Very good point.
To sequence the patient, although that certainly could be done. But
you're right, Sharon. That's right. So I think the ethical impetus here is that we should be studying affected individuals and their parents if they're not available. That's the requirement right now. So that's what we should be doing.
Is there a role for labs?
Yeah, I mean, there is, to the extent that laboratories can be relied upon to be sources of charitable contributions in kind. And in our, the lab I work with, we have done overseas studies of these kinds at very little to no expense to the people in that setting, in order to obtain this information, both for the benefit of those folks and others.
And I would say, and I have no relationship to Invitae, but I've given lectures. I lectured last year in the Middle East and North Africa Cancer Genetics Conference, and Invitae was the lab mentioned most often by those countries. And that was also true in a talk I gave recently in Asia. So I would say your company has done a lot more international outreach than some of the others. So that, I think this has been a fascinating topic. And I guess, Bob, this is still taught, I think, in genetic counseling programs, right?
Yes,
Is there discussion? I mean, NSGC is in a couple of weeks, right? Is there discussion about this kind of idea?
I'm giving this talk at NSGC.
Oh, all right.
But I think that counselors rely upon guidelines to feel comfortable that they're delivering the best care they can. And while this is still in there, and it's really 20 years old and I think inappropriate. They're going to continue to do that until convinced otherwise.
Okay, well, thank you so much.
Thank you.
This was really a great forum.
It was a
Really
pleasure. Thanks for asking me. I really had a good time. Appreciate it.
Okay. Okay, Clarissa, do you want to just mention the upcoming schedule in our last minute, or we're out of time, but if you just want to say.
Yeah, we're pretty much out of time, but we look forward to seeing you guys all back in the first Monday of December. Steve Mack is going to be speaking about HLA.
Great. Thanks, everyone.